So in this final video, we're going to look at charging a capacitor over a fixed resistor. So remember, in our previous videos, we looked at discharging a capacitor. We've charged up a capacitor, and then we've flipped some sort of switch, as we can see here. And then we would have charged up this capacitor by having this switch closed here, and then we would have transferred our switch over, and that would have let the capacitor discharge over this fixed resistor. Now we're going to think about the opposite way. We're going to think about when we're charging it up, and how the charge varies on capacitor there as we charge it. And the reason why we've kind of done it discharging than charging is because it's a little bit easier to do it discharging, and we can actually use some of the solutions we found previously to get the answer here. So when we charge our capacitor with this, some fixed resistance in the circuit, the current in the circuit again decreases until the potential difference across the capacitor has the same as the PD across the cell. Why is that? Well, we know that we've got this fixed potential difference across our cell here. That's going to make a current flow in our circuit. As that current flows in our circuit, we're going to build up charge on this capacitor, and that's going to cause a potential difference to form across our capacitor. But the thing is, that potential difference is going to oppose the potential difference from our cell, the electromotive force of our cell. And so the net EMF, if you like, if you think about combining this cell with this capacitor, is going to be, well, we're going to have a sort of V0 minus V, because we've got a potential difference of V0 here that's applying this potential difference to our circuit. So it's counteracted by this potential difference of V, and therefore the total potential difference we're actually going to have drop over our component here, this R, is going to be the difference between them, this V0 minus V. And so the current in our circuit is going to be given by this V0 minus V over the resistance. Remember, we saw this, we briefly spoke about this previously. But then what does that mean? Well, we know that this V increases as the charge on it builds up. As we build up more and more charge, the potential difference across our capacitor increases. That means the current is going to decrease, because we see that as this V gets bigger, this V0 minus V gets smaller, and therefore the current in our circuit decreases. And eventually we're going to get to the point where V0 is just equal to, or rather V is equal to V0, and we've got the same potential difference across this capacitor as you across our cell, and then no current will flow, and then our current will go to zero. So when we do that, what are the solutions for our circuit when we charge the capacitor through a fixed resistor? So what are the actual solutions? Well, we know that actually, if you think about it, the current behaves exactly as when we're discharging. Now, why is that? Well, the current only depends on the difference between the potential difference across this cell and the potential difference across this capacitor. So the current is just proportional to the net potential difference. But remember, if we think about it, originally this V is 0. And then our net potential difference is just this V0, and eventually this potential difference across this capacitor becomes V0, and so our net potential difference is 0. Therefore, we have a potential difference that the net potential difference starts at V0.
Hey guys, to continue watching this video and unlock hundreds of other super concise and exam board specific A-level physics videos, just click the Snap Revise smiley face. Join me today, and together let's make A-level physics a walk in the park.